At more than 5,000 meters above sea level, where the air holds almost no moisture, the sky stretches vast and unbroken, a canvas of stars that seem impossibly close. There, resting quietly against the silence, the Atlas telescope continued its nightly routine. Hour after hour, it scanned the heavens, searching for faint specks of light that might betray the presence of asteroids on dangerous paths toward Earth. It was designed to be a sentinel, a safeguard for humanity. Yet, on this night, Atlas found something far different from what it was built to catch. Its instruments detected a signal, a trace of light that did not fit the expected pattern. It was subtle at first, almost easy to miss, but unmistakably unusual. What it revealed was not a threat, but a mystery. And before we step further into this story, let me pause for just a moment. I am the Sleeping Professor, your companion through these quiet journeys. You're watching The Sleeping Professor, a place where we explore the universe slowly, carefully, and always with wonder. Chapter 1. A Visitor from the Stars. Imagine opening a book written in a language older than any civilization. Its pages are not parchment, but the night sky itself, its words written in light. Each star, each streak across the darkness, is a sentence in a cosmic story. On that July evening, Atlas turned one such page, and in doing so, uncovered the mark of a traveler from beyond our sun's reach. Astronomers named it 3I Atlas, the third interstellar object ever known to pass through our solar system. Only twice before had humanity encountered such wanderers. The first, in 2017, was the enigmatic Oumuamua, a long, tumbling shard whose strange acceleration baffled scientists and sparked endless debate. 2 years later came Borisov, a comet-like body, with a more familiar appearance, trailing a tail of gas and dust. Both passed swiftly, staying only briefly in our skies before vanishing into the dark. And now, this newest arrival, 3I Atlas, has joined that tiny register of cosmic guests, offering us another chance to glimpse what lies beyond our home. These encounters remind us of something profound. Our solar system is not sealed off from the galaxy. It is not a lonely island adrift in emptiness. It is more like a harbor, visited now and then by ships whose journeys began on shores we cannot see. Each one carries with it the fingerprints of distant worlds, silent messengers from places we may never reach. Together, we will trace the path of this newest visitor, considering not only what it is, but what it means. For in its presence, fleeting though it may be, lie questions that reach far beyond science. Questions about our place in a galaxy that is endlessly wider and older than we can easily imagine. Close your eyes for a moment and picture yourself standing in your backyard on a still evening. The stars above shimmer like scattered diamonds. Almost every one of those points of light belongs to our neighborhood. Stars bound to the same spiral arm of the Milky Way that holds our sun. The planets we know, too, are family. Siblings of Earth, born billions of years ago from the same cloud of dust and fire. But 3I Atlas is different. It is not kin. It is not shaped by the same forces that gave birth to us. It is in the most literal sense alien. It formed around another star, perhaps in another cluster of stars, under physical conditions unlike those of our solar system. To study it is to peer across an almost unimaginable gulf, to hold in our telescopes a fragment of a history that unfolded light years away. The discovery itself feels almost like accident, though it was anything but. Atlas, the asteroid terrestrial impact last alert system, was built with vigilance in mind. Its purpose is defense, to serve as an early warning network for rocks that might one day strike our planet. But on that July morning, it gave us something far more poetic. A messenger arriving unannounced, carrying whispers from another world. When astronomers first noticed the faint mark of 3I Atlas against the backdrop of stars, they realized quickly that it was not ordinary. The laws of celestial mechanics are strict and unforgiving. Bodies bound to our sun trace ellipses, closed loops that repeat endlessly, predictable to the second. But this object did not follow that rule. Its trajectory was hyperbolic, the mathematical signature of an outsider. It had come from far away, and once it crossed our sky, it would leave us forever. This is what makes interstellar visitors so rare and so precious. They are nomads of the galaxy, drifting freely between stars. For millions, even billions of years, they wander in silence, untouched by any one system's gravity. They endure stellar winds, cosmic radiation, and the slow grinding passage of time. That any of them should intersect with our tiny solar system, and that we should notice them during our brief moment of watching, feels almost like a miracle. Consider the odds. The Milky Way is vast beyond comprehension. Our solar system is less than a speck within it, a grain of dust in an ocean so wide that numbers lose their meaning. For 3 interstellar objects to pass through our neighborhood in such a short span of human history is extraordinary. It is as though we are standing on a lonely beach, and 3 separate bottles have washed ashore, each carrying a fragment of a letter from unknown senders. 3I Atlas now takes its place among these rare arrivals, a new entry in a cosmic guest book that for most of human history we didn't even know existed. Each name in that register, Oumuamua, Borisov, and now Atlas, represents more than just an astronomical discovery. They are symbols of our expanding curiosity, proof that with the instruments we have built, we can notice the faintest of signals and interpret their stories. And so, as we begin to trace the story of 3I Atlas, we must remind ourselves that this is not just about one object hurtling through our skies. It is about perspective. It is about opening a window to the wider galaxy and feeling, however briefly, the enormity of the distances that separate us from everything else. This object has traveled longer than we can imagine, across spaces more hostile than we can endure, and now, for a fleeting moment, it passes close enough for us to glimpse it. What questions does it bring? What answers might it hold? These are not simple curiosities. They are questions that cut to the heart of our understanding, of how common worlds like ours may be, of how material is exchanged across the galaxy, of how fragile and temporary our own existence might look from afar. As we will discover, the mystery of 3I Atlas may not lie in what danger it poses, but in what truths it forces us to confront. Truths that may be far more unsettling than any physical threat. Chapter 2. First Impressions, First Questions. In those first days after discovery, 3I Atlas existed in a kind of cosmic limbo. The initial observations showed a faint object moving through space, but confirming its true nature required careful calculation and patience. Astronomers around the world turned their instruments toward this new visitor, each observation adding another piece to an increasingly fascinating puzzle. The mathematics came first, as they always do in astronomy. Orbital calculations are humanity's way of reading the language of gravity, of understanding the invisible forces that govern celestial motion. When the numbers were finally crunched, they told an unmistakable story. This object's orbit was hyperbolic, with an eccentricity greater than 1. In the precise language of celestial mechanics, this was confirmation that 3I Atlas had come from interstellar space and would return there. Think of it like examining a visitor's passport. The orbital parameters were 3I Atlas cosmic credentials, proof of its exotic origins. Unlike the countless asteroids and comets that call our solar system home, this object bore the mathematical signature of a true outsider. Its trajectory was an open curve, a path that would carry it past our sun and back into the galactic void, never to return. The reaction from the astronomical community was a mixture of excitement and careful professionalism. After all, we'd been here before with Oumuamua and Borisov. Each interstellar visitor had brought its own surprises and puzzles. Oumuamua had accelerated mysteriously as it departed our solar system, defying easy explanation and sparking debates that continue to this day. Borisov had seemed more conventional, behaving like the comets we know from our own solar system, offering a reassuring sense of cosmic familiarity. But 3i Atlas promised to be different again. Early observations hinted at properties that didn't quite match either of its predecessors. It was larger than Oumuamua, but smaller than initially estimated for Borisov. Its brightness varied in ways that suggested rotation, a tumbling motion that spoke of its violent ejection from whatever star system had given it birth. Meanwhile, the broader public began to take notice. News outlets picked up the story, and social media buzzed with speculation. There's something deeply compelling about interstellar visitors. Perhaps it's the recognition that we're witnessing something genuinely rare and significant. In an age when astronomical discoveries are announced regularly, interstellar objects retain a special power to capture our collective imagination. The official statements from NASA and the European Space Agency came quickly, as they always do when a new celestial object makes headlines. The message was clear and reassuring. 3i Atlas posed no threat to Earth. Its closest approach would carry it no nearer than 1.8 astronomical units, roughly 270 million kilometers away. To put that in perspective, it would pass more than twice as far from Earth as Mars does at its closest approach. In cosmic terms, this was a distant flyby, a polite wave from a cosmic neighbor passing through. Yet even with these reassurances, something about 3i Atlas felt different from the start. Perhaps it was the timing of its discovery, coming at a moment when humanity was becoming increasingly aware of its place in a vast and potentially populated galaxy. Or perhaps it was simply the accumulation of mystery. 3 interstellar visitors in less than a decade, each one unique, each one raising new questions about the nature of the galaxy beyond our solar system. The early observations revealed an object that seemed almost deliberately enigmatic. Its spectrum showed characteristics that didn't quite match any known class of solar system objects. Its behavior, as it approached the Sun, suggested composition and structure that would challenge our understanding of how such objects form and survive their journeys through interstellar space. There was something almost theatrical about 3i Atlas timing. It would reach its closest approach to the Sun, its perihelion, just as it became impossible to observe from Earth, lost in our star's glare at the very moment when it might have revealed its most interesting secret. It was as if the universe had designed this visitor to tantalize us, to offer glimpses of its mysteries, while keeping its deepest secrets hidden in the solar glare. As those first weeks passed and more observations accumulated, it became clear that 3i Atlas would not be easily categorized. It wasn't quite like Oumuamua, with its strange acceleration and elongated shape. It wasn't quite like Borisov, with its conventional comet-like behavior. Instead, it was something new, something that would require astronomers to expand their understanding of what interstellar objects could be and do. The questions multiplied faster than the answers. Where had 3i Atlas come from? How long had it been traveling through the galaxy? What could its composition and behavior tell us about conditions in other star systems? And perhaps most intriguingly, what were the odds that 3 such different objects would visit our solar system in such a relatively short span of time? As we watched 3i Atlas approach its date with the Sun, there was a growing sense that this visitor might have more to teach us than we were prepared to learn. Chapter 3. What lies in a trajectory? To understand what makes 3i Atlas so special, we need to take a moment to appreciate the elegant mathematics of celestial motion. Imagine orbits as cosmic highways, invisible paths carved by gravity through the three-dimensional ocean of space. Most of the objects in our solar system travel on closed loops, ellipses that carry them around the sun in endless cycles, bound forever by our star's gravitational embrace. These elliptical orbits are like cosmic racetracks, oval paths that bring planets, asteroids, and comets close to the sun, and then carry them back out into the cold, only to return again and again across billions of years. The mathematics that describe these paths were first understood by Johannes Kepler 4 centuries ago, and they reveal a universe of clockwork precision where every celestial body follows its appointed course with mathematical certainty. But 3i Atlas travels a different kind of path entirely. Its orbit is hyperbolic, not a closed loop, but an open curve that sweeps through our solar system once and never returns. Imagine the difference between a highway that circles a city and a straight road that passes through it. The circular highway keeps traffic moving in an endless loop, while the straight road allows travelers to pass through and continue to distant destinations. In the language of orbital mechanics, this difference is captured by a number called eccentricity. Circular orbits have an eccentricity of 0. Perfect, endless loops. Elliptical orbits have eccentricities between 0 and 1, stretched ovals that still close upon themselves. But hyperbolic orbits have eccentricities greater than 1, and these are the mathematical signatures of objects that are just passing through. When astronomers calculated 3i Atlas eccentricity and found it significantly greater than 1, they were seeing cosmic proof of its alien origins. This wasn't a number that could lie or be misinterpreted. It was as definitive as a passport stamp. Mathematical evidence that this object had come from somewhere else and was bound for somewhere else entirely. The hyperbolic trajectory tells us something profound about 3i Atlas' journey. It speaks of immense speeds and vast distances, of an object moving so fast that our sun's gravity, powerful enough to hold Jupiter in its orbit at nearly 800 million kilometers, cannot capture this visitor and make it stay. Instead, the sun's gravity simply bends 3i Atlas' path, curving its straight-line journey through interstellar space into a gentle arc that carries it around our star and back into the galactic void. Think of it like a stone skipping across the surface of a pond. The stone doesn't become part of the pond. It touches the surface, interacts briefly with the water, and then continues its journey beyond. 3i Atlas is skipping across the gravitational surface of our solar system, touching our realm of space briefly before continuing its billion-year journey through the galaxy. This hyperbolic trajectory also tells us something about 3i Atlas' speed. It's moving fast, very fast by the standards of objects in our solar system. While our planets lumber around the sun at speeds measured in tens of kilometers per second, 3i Atlas is racing through space at more than 60 kilometers per second. That's fast enough to travel from Earth to the Moon in less than 2 hours. A velocity that speaks of the violent processes that likely ejected it from its home system eons ago. The mathematics of hyperbolic orbits reveal other secrets as well. They allow astronomers to trace 3i Atlas' path backward through time, to calculate roughly where it came from, and when it began its interstellar journey. These calculations suggest origins in the galactic thick disk, a region of older stars that formed when our galaxy was younger and more chaotic. The numbers paint a picture of an object that has been wandering through space since before our solar system even existed. There's something almost melancholy about hyperbolic trajectories when you contemplate them deeply. They represent ultimate loneliness, eternal wandering through the vast emptiness between stars, while the planets and moons of our solar system enjoy the constant companionship of their stellar family. 3i Atlas travels alone through the cold and dark, carrying whatever memories it might hold of its distant birthplace toward an unknowable future. Yet, There's also something beautiful about these open curves. They represent freedom from gravitational bondage, independence from any single star's influence. 3i Atlas is a citizen of the galaxy itself, not tied to any particular stellar system, but belonging to the vast community of stars that make up the Milky Way. As we watch 3i Atlas follow its hyperbolic path through our solar system, we're witnessing a kind of cosmic choreography, a dance between visitor and host star that follows the ancient laws of physics with perfect precision. The trajectory is more than just a path through space. It's a story written in mathematics, a tale of origins, journey, and destiny that spans billions of years and countless light years of distance. Understanding this trajectory helps us appreciate just how remarkable it is that we're able to observe 3i Atlas at all. The window of opportunity for studying interstellar visitors is always brief. They appear from the darkness, pass through our solar system in a matter of months or years, and then vanish back into the galactic void. We are incredibly fortunate to live in an age when our technology allows us to spot these rare visitors and decipher the stories written in their paths through space. Chapter 4. Setting aside impact fears. When news of any new cosmic visitor reaches the public, there's often an undercurrent of anxiety that ripples through social media and news coverage. It's understandable. Our cultural imagination has been shaped by countless science fiction stories of killer asteroids and extinction-level events. The dramatic impact that ended the age of dinosaurs 66 million years ago has become a touchstone for cosmic catastrophe, a reminder that space can be a dangerous neighborhood. But 3i Atlas presents no such threat, and understanding why can actually be quite comforting. The numbers tell a clear and reassuring story. At its closest approach to Earth, 3i Atlas will pass no nearer than 1.8 astronomical units, approximately 270 million kilometers away. To put this vast distance in perspective, consider that Mars at its closest approach to Earth is about 55 million kilometers away. 3i Atlas will pass nearly 5 times farther away than our closest planetary neighbor ever comes. Imagine standing at one end of a football field and trying to hit a target at the other end with a baseball. Now imagine that the football field is actually 5,000 kilometers long. That's roughly the scale we're dealing with when we talk about 3i Atlas flyby. In the context of our solar system, this is an exceptionally distant encounter, polite and respectful, like a neighbor waving from across a very wide street. The orbital calculations that determine this safe distance aren't guesswork or rough estimates. They're based on precise mathematical principles that have been tested and verified countless times in our exploration of the solar system. The same physics that allow us to send spacecraft to distant planets with pinpoint accuracy also tell us exactly where 3i Atlas will be at any given moment. There's no uncertainty here, no hidden variables that might suddenly alter its trajectory. This precision is part of what makes modern planetary defense so effective. NASA Planetary Defense Coordination Office exists specifically to track objects that might pose a threat to Earth, and they've developed sophisticated systems for detecting, tracking, and, if necessary, deflecting potentially dangerous asteroids. The recent success of the DART mission, which successfully altered the orbit of the asteroid Dimorphos, demonstrates that we're not helpless in the face of cosmic threats. But 3i Atlas doesn't even register on the scale of objects that planetary defense experts worry about. True, potentially hazardous asteroids are defined as objects larger than 140 meters that pass within 7.5 million kilometers of Earth's orbit. 3i Atlas is passing more than 35 times farther away than this already generous safety margin. In the careful language of impact risk assessment, 3i Atlas has exactly zero probability of collision with Earth. There's something psychologically interesting about why interstellar objects seem to trigger more anxiety than ordinary asteroids. Perhaps it's the word interstellar itself, which carries connotations of the unknown and potentially threatening. Or perhaps it's the recognition that these objects are truly alien, products of environments and processes we don't fully understand. There's an instinctive wariness about strangers, even cosmic ones. Oumuamua experienced this same phenomenon when it was discovered in 2017. Despite being on a trajectory that posed no threat to Earth, its unusual properties and mysterious behavior spawned countless theories about its nature and origins. Some of these theories verged on science fiction, suggesting artificial origins or deliberately engineered properties. The reality, as is often the case in astronomy, proved to be both more mundane and more wonderful than the wildest speculations. With 3I Atlas safely ruled out as an impact threat, we're free to focus on what makes it truly interesting. The worst-case scenario in the title of our exploration isn't about physical danger to our planet. Earth will continue its ancient dance around the Sun, unperturbed by this distant visitor. The real significance of 3E Atlas lies not in any threat it might pose to our physical safety, but in the questions it raises about our understanding of the cosmos and our place within it. This shift in perspective, from fear of collision to fascination with discovery, represents a kind of maturation in our relationship with the universe. We're learning to see interstellar visitors, not as potential threats, but as rare opportunities to expand our knowledge and challenge our assumptions. Each one carries information from distant parts of the galaxy, offering glimpses into stellar systems and cosmic processes that we might otherwise never encounter. The safety of 3I Atlas passage allows us to appreciate it purely as a scientific phenomenon, free from the anxiety that might cloud our judgment if it posed any real danger. We can watch its approach with the calm attention of researchers, rather than the nervous vigilance of potential victims. This mental space, this freedom from fear, is essential for the kind of careful, open-minded investigation that 3I Atlas deserves. As we settle into the comfortable knowledge that 3 Atlas poses no physical threat to our world, we can begin to explore the more subtle and perhaps more significant ways in which this cosmic visitor might challenge our understanding of reality. The true worst-case scenario, as we'll discover, has nothing to do with impact craters, and everything to do with the collision between assumption and evidence, between what we thought we knew and what the universe is actually showing us. Chapter 5. Ancient Traveler. Time takes on a different meaning when we contemplate objects like 3I Atlas. While human civilization measures its history in thousands of years, and our species has existed for mere hundreds of thousands, this cosmic wanderer has been traveling through the galaxy for billions of years. To truly appreciate 3I Atlas, we need to stretch our imagination across spans of time so vast they challenge our ability to comprehend them. Current models suggest that 3I Atlas likely originated from what astronomers call the galactic thick disk, a region of space populated by older stars, stellar veterans that formed when our galaxy was younger and more chaotic. These ancient suns and their planetary systems date back to an era when the Milky Way was still finding its shape, when stellar nurseries were more violent and star formation proceeded at a faster, more turbulent pace. The thick disk represents a chapter in galactic history that predates our own solar system by billions of years. When these older stars were forming, the region of space that would eventually give birth to our Sun was still a sparse collection of gas and dust, unremarkable and largely empty. The elements that would eventually form Earth, the carbon, oxygen, and silicon in our bodies and our world, were still being forged in the nuclear furnaces of distant stars, waiting to be scattered into space by supernova that wouldn't occur for eons. 3I Atlas may have witnessed this entire process. If current estimates are correct, It could be older than our solar system's 4.6 billion year history. This ancient wanderer might have been ejected from its home system before Earth even existed, beginning its lonely journey through interstellar space, while our region of the galaxy was still awaiting the gravitational collapse that would eventually create our sun and planets. Imagine the perspective this cosmic traveler might have. If objects could have memories, it would have seen our sun ignite for the first time, watched the rocky planets accrete from the primordial disk of dust and gas, observed the late heavy bombardments that scarred the young worlds with countless impact craters. It would have been drifting through space when the first life appeared in Earth's ancient oceans, when photosynthesis began to change our planet's atmosphere, when complex cells evolved and multicellular life took hold. The journey itself staggers the imagination. Traveling at its current speed of about 61 kilometers per second, 3 Atlas covers roughly 1.9 billion kilometers per year, a distance greater than the diameter of Saturn's orbit. Yet even at this tremendous velocity, crossing the galaxy would take hundreds of millions of years. The spaces between stars are so vast that even objects moving at interstellar speeds become test pilots for eternity, carrying their secrets across distances that make our solar system seem like a small neighborhood. During its eons-long journey, 3I Atlas would have encountered cosmic phenomena that we can only imagine. It may have passed through the shockwaves of supernova, those stellar explosions that enrich the galaxy with heavy elements and compress surrounding gas clouds into new stellar nurseries. It might have drifted through the spiral arms of our galaxy multiple times, experiencing regions of space where star formation is active and stellar winds. Interstellar space isn't empty. It's filled with radiation, cosmic rays, and sparse but persistent gas and dust. Over billions of years, these forces could erode away layers of material, alter surface chemistry, and gradually wear down even the most durable objects. Yet 3I Atlas has endured, preserving within its structure a record of conditions that existed when our galaxy was fundamentally different than it is today. This preservation of ancient material makes interstellar objects like 3I Atlas incredibly valuable to science. They're time capsules from epochs we can study in no other way, carrying within their composition and structure information about stellar systems and galactic conditions that existed billions of years ago. Every measurement we make, every spectrum we capture, adds to our understanding of how galaxies evolve and how planetary systems form under different conditions than those that created our own solar system. There's something profoundly humbling about contemplating 3I Atlas' age and journey. While human history, all of recorded civilization, all of our wars and discoveries and cultural achievements, represents just a few thousand years, this object has been wandering through space since before complex life existed on Earth. It connects us to deep time, to the ancient history of our galaxy, in a way that few other objects can. The thick disk origins also tell us something important about galactic evolution. The stars and planetary systems of this older population formed under different conditions than our Sun's more recent stellar neighborhood. They had access to different mixtures of elements, different gravitational environments, different rates of stellar formation and destruction. 3 Dunzes carries with it chemical and physical signatures of these ancient conditions, offering us a direct sample of how worlds formed when our galaxy was young. As we watch this ancient traveler pass through our modern solar system, we're witnessing a kind of temporal bridge, a connection between the deep past of our galaxy and its present moment. 3 Atlas has survived longer than mountain ranges, longer than continents, longer than the complex biosphere that makes Earth unique. It represents persistence, on a scale that challenges our human-centered perspective on permanence and change. Chapter 6. A Survivor Against Odds. The mere existence of 3I Atlas represents a triumph against almost impossible odds. To appreciate this fully, we need to understand just how hostile the galaxy can be to small, wandering objects, and how many ways there are for an interstellar traveler to meet its end during a billion-year journey through space. Consider first the violence of its likely origins. 3I Atlas didn't choose to leave its home system. It was almost certainly ejected by gravitational interactions so powerful they could fling an object of its size completely out of its stellar neighborhood. This could have happened through a close encounter with a massive planet, like Jupiter in our own solar system, which has been known to act as a gravitational slingshot capable of sending smaller objects into hyperbolic escape trajectories. Alternatively, 3I Atlas might have been scattered by the death throes of its parent star. When massive stars explode as supernova, they can disrupt entire planetary systems, hurling planets, asteroids, and comets into interstellar space with tremendous violence. Or perhaps it escaped during the chaotic dance of a close stellar encounter, when its home star passed near another star, and the competing gravitational fields tore apart the carefully ordered architecture of orbiting worlds. Whatever the mechanism, the ejection process itself should have been traumatic enough to destroy most objects. The gravitational stresses involved in accelerating to interstellar velocities are enormous, capable of tearing apart any but the most cohesive bodies. That 3I Atlas survived this violent birth into wandering suggests either exceptional internal strength or simply extraordinary luck, but surviving ejection was only the beginning. Once in interstellar space, 3I Atlas entered an environment that, while sparse, is far from empty. Cosmic radiation streams through the galaxy at nearly the speed of light. High-energy particles capable of gradually altering surface chemistry and structure. Over billions of years, this constant bombardment should have eroded layers of material from 3I Atlas' surface, possibly changing its composition and certainly affecting its appearance. The interstellar medium itself, though incredibly tenuous, presents another slow but persistent threat. Space between stars contains roughly 1 atom per cubic centimeter. A vacuum better than anything we can create on Earth, but still dense enough to matter over cosmic distances and timescales. An object moving at 61 kilometers per second through this medium experiences a constant, gentle pressure that, over eons, could strip away volatile materials and gradually alter its trajectory. Then there are the larger hazards. Encounters with gas clouds, passage through spiral arms where stellar activity is higher, and the shock waves from distant supernova. Each of these events could have damaged or destroyed 3I Atlas, yet it has somehow navigated them all. The object we observe today has run a gauntlet of cosmic hazards that spans billions of years and countless light-years of space. Current estimates place 3I Atlas somewhere between 300 meters and 5 kilometers in diameter. Small enough to be vulnerable to disruption, large enough to have survived the journey intact. This size range itself tells a story of survival, suggesting an object substantial enough to hold together under stress, but not so massive as to be immune to ejection from its original system. It occupies a kind of sweet spot in the physics of interstellar wandering. The chemistry preserved within 3AU is equally remarkable. Spectroscopic observations reveal molecules and compounds that should be fragile over cosmic timescales, yet have somehow been preserved during its billion-year journey. It's like finding a library book that has somehow survived intact after being buried in a desert for geological ages. The preservation itself becomes almost as interesting as the content. This survival raises intriguing questions about the internal structure and composition. High velocities require high-energy ejection mechanisms, violent events capable of imparting tremendous kinetic energy to objects as they're hurled into interstellar space. The most straightforward explanation involves gravitational slingshots of extraordinary power. In our own solar system, we've learned to use Jupiter's massive gravitational field to accelerate spacecraft to the outer reaches of the solar system and beyond. The Voyager probes, New Horizons, and other missions have all borrowed energy from planetary encounters to achieve the velocities needed for their extended journeys. But to reach the speeds we observe in 3I Atlas, we need to imagine slingshot encounters with objects far more massive than Jupiter, or multiple interactions that compound their effects. Alternatively, 3I Atlas might owe its speed to stellar violence of a more dramatic nature. When massive stars explode as supernova, they release energy equivalent to the Sun's entire lifetime output in a matter of seconds. These explosions can disrupt entire star systems, flinging planets and smaller bodies into space with tremendous velocity. An object accelerated by such a cataclysmic event might well achieve the speeds we observe in 3I Atlas. There's also the possibility of ejection during stellar encounters. Those rare cosmic events when two star systems pass close enough to gravitationally disrupt each other. During such encounters, the competing gravitational fields can accelerate objects to extreme velocities as they're torn away from their original orbits. These encounters are more common in dense stellar environments, such as globular clusters or the galactic center, where stars are packed more closely together than in our galactic neighborhood. But the speed of 3I Atlas raises another more subtle question. Are we seeing the beginning of a pattern? 3 interstellar visitors in less than a decade might seem like a small sample size, but the progression in their velocities, 26, 32, and now 61 kilometers per second, could hint at something more systematic than random chance. Are we perhaps entering a region of the galaxy where faster-moving interstellar objects are more common? Our solar system orbits the galactic center at about 220 kilometers per second, carrying us through different neighborhoods of the galaxy over millions of years. As we move through these regions, we might encounter different populations of interstellar objects, some ejected by nearby stellar activity, others that have been wandering the galaxy for billions of years. The velocities of these objects could serve as signatures of their origins and the processes that set them free. There's also the intriguing possibility that higher velocity objects are simply more noticeable. Faster-moving visitors spend less time in our solar system, but they also undergo more dramatic changes in brightness and apparent motion that make them easier to detect against the stellar background. We might be developing an observational bias toward high-speed travelers, seeing them more readily than their slower, more leisurely cousins. This speed also affects what we can learn from 3I Atlas during its brief visit. Faster objects spend less time within range of our telescopes, providing shorter observation windows for detailed study. While Oumuamua remained observable for several months and Borisov for over a year, 3 Skoi's high velocity means its appearance in our skies will be correspondingly brief. We have less time to gather data, fewer opportunities to understand its composition and structure. The velocity of 3I Atlas also tells us something about the energy budget of galactic dynamics. Objects moving at such speeds carry enormous kinetic energy that had to come from somewhere. Understanding how the galaxy produces populations of high-velocity wanderers helps us comprehend the broader processes that shape stellar systems and drive galactic evolution. Perhaps most intriguingly, the speed of 3I Atlas connects to questions about the frequency of interstellar visitors. If high-velocity objects are more common than we previously thought, it might suggest that violent ejection processes, supernova, stellar encounters, planetary disruption, are more frequent or more effective at producing interstellar wanderers than our models predict. We might be living in a galaxy that's more dynamically active than we realized. where the peaceful neighborhood of our solar system is actually surrounded by a vast population of cosmic refugees fleeing stellar violence. As we watch 3I Atlas race through our solar system, we're not just observing its trajectory, but glimpsing the complex dynamics that govern how objects move between star systems. Its speed is both a clue to its origins and a challenge to our understanding of how the galaxy operates on the largest scales. Chapter 8. Vanishing Interstellar Glare. There's a certain poetic tragedy to the timing of 3I Atlas' closest approach to our Sun. Like a cosmic visitor who chooses to whisper their most important secrets just as they step into shadow, 3I Atlas will reach its perihelion, its closest point to our star, precisely when it becomes impossible for us to observe it from Earth. This isn't coincidence or cosmic cruelty. It's simply the geometry of solar observation and the limitations of our Earth-bound perspective. As 3I Atlas sweeps closer to the Sun, it enters what astronomers call the zone of solar conjunction, a region of sky where our star's overwhelming brightness makes detailed observation nearly impossible. Even the most powerful telescopes on Earth cannot peer into the solar glare to study objects that pass too close to our star's apparent position in the sky. It's like trying to observe a candle flame while staring directly into a searchlight. The brilliant foreground simply overwhelms any fainter background objects. This observational blackout comes at the most scientifically interesting moment of 3I Atlas visit. Perihelion is when interstellar visitors typically become most active, when the Sun's heat begins to sublimate volatile materials from their surfaces and potentially reveal their internal composition. This is the moment when comets develop their characteristic tails, when icy materials vaporize and create the spectacular displays that have captivated human observers for millennia. For 3I Atlas, perihelion represents the climax of its solar encounter, the point where our star's energy will have the greatest effect on its surface and internal structure. Any volatile materials, water, ice, carbon dioxide, or more exotic compounds, might begin to outgas, creating temporary atmospheres or even visible comas that could tell us volumes about the object's composition and origins. These are precisely the phenomena that astronomers most want to study, the revelations that could unlock the mysteries of this ancient wanderer. Yet at this crucial moment, 3I Atlas will be lost to us, hidden in the Sun's glare like a secret whispered in a thunderstorm. The irony is profound. We can study this cosmic visitor as it approaches, tracking its motion and analyzing its spectrum, while it remains in the darkness of space. But just when it might reveal its most intimate properties, it vanishes behind the veil of solar brilliance. This limitation affects ground-based observatories around the world. Even telescopes equipped with sophisticated coronagraphs, instruments designed to block the Sun's direct light, cannot penetrate the region where 3I Atlas will pass. The scattered light from our stars' extended atmosphere creates a zone of observational impossibility that extends several degrees around the solar disk, easily encompassing the trajectory of our interstellar visitor. Space-based observations face similar challenges, though some solar monitoring satellites might catch glimpses of 3I Atlas as it passes through their fields of view. These observations, if they occur, would be brief and limited, snapshots rather than the detailed, long-term studies that reveal an object's true nature. It's like trying to understand a person's character from a single photograph taken in passing. The timing of this observational gap raises subtle questions about cosmic coincidence. Is it merely chance that 3I Atlas reaches its most active phase just as it becomes unobservable? Or might there be deeper connections between the physics of solar encounters and the limitations of observation that make such timing more common than we might expect? Consider the perspective of 3I Atlas itself during this phase of its journey. After billions of years in the cold emptiness of interstellar space, it suddenly finds itself bathed in the warmth and radiation of a star. Surface temperatures that have remained constant for eons begin to rise. Frozen materials that have been stable since its ejection from its home system might begin to change phase, sublimating directly from solid to gas in the near vacuum of space. These changes could reveal the object's internal structure and composition in ways that no amount of remote observation could achieve. As surface layers heat and potentially sublimate away, deeper materials might be exposed. Ancient ices and compounds that have been protected from cosmic radiation and interstellar weathering throughout 3I Atlas' long journey. The perihelion passage might literally peel back layers of history, revealing the object's primordial composition. But we'll miss most of this revelation, forced to infer from before and after observations what might have happened during the crucial hours or days when 3I Atlas was closest to the Sun. Wanden Martas barn or the tejustamid forced to infer. It's like being asked to determine what happened during a theatrical performance by examining the stage before the curtain rises and after it falls, with no view of the actual drama that unfolds between. This observational limitation also affects our ability to compare 3I Atlas with its interstellar predecessors. Both Oumuamua and Borisov provided surprises during their closest solar approaches. Oumuamua's mysterious acceleration and Borisov's conventional but informative comet-like behavior. The both adopt Fiboacus Orbuzarezed Farladas Divil Diverse Burzar. What surprises might 3I Atlas have in store during its own perihelion passage? We may never know, or we might have to piece together the story from subtle clues observable only after the fact. The vanishing of 3I Atlas into solar glare serves as a reminder of the limitations and frustrations inherent in astronomy. We are observers of a universe that doesn't always cooperate with our desire to understand it. Sometimes the most interesting events occur precisely when we cannot observe them, leaving us to wonder about cosmic dramas that unfold just beyond the reach of our instruments and techniques. Yet there's also something fitting about this cosmic hide-and-seek. 3I Atlas has spent billions of years traveling through the darkness between stars, and perhaps it's appropriate that its moment of greatest revelation should occur in the one place we cannot follow. Some cosmic secrets, it seems, are meant to remain hidden in the light. Chapter 9. The chemistry that shouldn't be when the James Webb Space Telescope turned its infrared gaze toward 3I. It revealed something that stopped astronomers in their tracks. The spectroscopic data showed an object dominated by carbon dioxide, roughly 81% CO2 compared to water vapor. A composition so unusual that it challenged fundamental assumptions about how icy bodies form and evolve in the cosmos. To understand why this discovery is so startling, we need to appreciate what normal looks like in the realm of comets and icy bodies. Throughout our solar system, from the great comets that sweep in from the Oort cloud to the small icy moons of the outer planets, water ice is king. H2O dominates the composition of these objects, because water is both abundant in the universe and relatively easy to condense from the primordial clouds that form planetary systems. When early astronomers first detected water vapor in comet tails, it confirmed theoretical predictions about how these objects should be composed. The dirty snowball model of comets, chunks of ice and rock left over from the formation of the solar system, has served astronomy well for decades. Water ice, with smaller amounts of carbon dioxide, methane, and other volatiles, seemed to be the universal recipe for icy bodies wherever they formed. But 3I Atlas appears to have been made from a different recipe entirely. The carbon dioxide dominance observed by Webb suggests formation conditions unlike anything we see in our own solar system. In the cold outer regions where comets typically form, water condenses more readily than CO2, leading naturally to water-dominated compositions. For carbon dioxide to dominate requires either very different temperature and pressure conditions during formation or subsequent processing that altered the original composition. The discovery sent astronomers scrambling through the literature, searching for precedents and mechanisms that might explain such unusual chemistry. They found a few hints. Rare solar system objects like the comet C2016 R2 Pan-STARRS, which showed unusually high CO2 content, and some asteroids with carbon-rich surfaces, but nothing quite like the extreme composition observed in 3I Atlas. Several natural explanations have been proposed, each offering a different window into the exotic conditions that might create such an object. One possibility involves the CO2 snowline, the distance from a star where carbon dioxide can condense from gas to solid. In some stellar systems, particularly those with different masses or evolutionary histories than our Sun, this snowline might occur in regions where planetary formation is active, leading to CO2-dominated bodies. Another explanation involves radiation processing during 3I Atlas' billion-year journey through space. Cosmic rays and ultraviolet radiation could gradually alter surface chemistry, potentially converting water ice to other compounds, or preferentially removing certain materials while preserving others. Over cosmic timescales, these processes might transform an originally water-rich object into the carbon dioxide-dominated body we observe today. There's also the intriguing possibility of subsurface differentiation. Perhaps 3I Atlas formed with a more conventional composition, but internal heating from radioactive decay or tidal interactions caused chemical separation within the object. Denser materials might have settled inward, while lighter, more volatile compounds migrated to the surface, creating the unusual surface chemistry detected by our instruments. The precision of the Webb observations allows astronomers to rule out some explanations while highlighting others. The 81% Q2 to H2O ratio isn't just unusual. It's so extreme that it suggests either very specific formation conditions or very specific evolutionary processes. This isn't a minor deviation from expected composition. It's a complete inversion of what we normally observe. This chemical anomaly also raises questions about the stellar system where 3I Atlas originated. Different types of stars create different environments for planetary formation. Older, metal-poor stars might have had different ratios of available elements. Stars with different masses or evolutionary paths could have created temperature and pressure conditions that favored CO2 over water ice formation. 3I Atlas might be carrying chemical signatures that tell us about stellar environments, unlike anything in our local galactic neighborhood. The implications extend beyond simple composition to fundamental questions about planetary formation processes throughout the galaxy. If objects like 3I Atlas are common in certain stellar environments, it suggests that our solar system's water-dominated chemistry might be less universal than we assume. The galaxy might host a vast diversity of chemical environments, each producing its own distinctive population of planets, asteroids, and comets. From an astrobiological perspective, the CO2 dominance of 3I Atlas is particularly intriguing. While water is considered essential for life as we know it, carbon dioxide plays important roles in many biological processes. An object with such extreme CO2 content might represent conditions where different forms of chemistry, perhaps even different forms of life, could develop. It's a reminder that the universe might be far more chemically diverse than our water-centric perspective suggests. The detection also showcases the remarkable capabilities of modern astronomical instruments. The ability to analyze the chemical composition of a small object billions of kilometers away, moving at tremendous speed through space, represents a triumph of both technology and technique. Yet even with these capabilities, 3i Atlas keeps its secrets carefully guarded, revealing just enough to intrigue us while maintaining an aura of cosmic mystery. As we contemplate this chemical anomaly, we are forced to confront the possibility that 3i Atlas represents something genuinely new in our experience, an object whose composition challenges our understanding of how icy bodies form and evolve. Whether this unusual chemistry results from exotic formation conditions, billion-year processing in interstellar space, or something even more mysterious remains an open question, one that may reshape our understanding of planetary formation throughout the galaxy. Chapter 10: Messages in Molecules. As we delve deeper into the unusual chemistry of 3i Atlas, a provocative question begins to emerge from the realm of speculation. Could such an extreme and specific composition be intentional? This isn't a suggestion of little green beings engineering cosmic visitors, but rather a more subtle consideration of whether advanced civilizations might use chemistry itself as a form of galactic communication. The idea builds on decades of thinking about SETI, the search for extraterrestrial intelligence, and the various ways that advanced civilizations might attempt to communicate across interstellar distances. Traditional SETI focuses on radio signals, optical pulses, or other forms of electromagnetic communication. But some theorists have suggested more exotic possibilities, messages encoded in the structure of matter itself, carried by objects that travel between star systems over cosmic timescales. Consider the advantages of molecular messaging. Unlike radio signals, which fade with distance and can be blocked by interstellar dust and gas, physical objects carry their information intact across any distance. Unlike electromagnetic communications, which travel at light speed but exist only briefly at any given location, material messengers persist in space and time, potentially detectable for millions of years after their creation. The 81% carbon dioxide composition of 3i Atlas is so unusual, so far from what we expect in natural icy bodies, that it almost seems designed to attract attention. It's like finding a book in a library where every page contains the same rare word repeated in precise patterns, so statistically unlikely that it demands explanation. Could this extreme composition be a cosmic calling card? A signature meant to distinguish artificial or modified objects from their natural counterparts. This speculation draws inspiration from theoretical frameworks like the Fermi paradox and the various solutions proposed to explain why we haven't detected obvious signs of alien intelligence. Perhaps advanced civilizations don't broadcast radio signals into space, but instead embed their signatures in matter itself. In the isotopic ratios of wandering asteroids, in the molecular composition of interstellar objects, in patterns too specific and unlikely to be natural. The chemistry of 3i Atlas could represent what astrobiologists call a biosignature, but not one produced by life directly. Instead, it might be a technosignature, evidence of technological intelligence that has learned to manipulate matter on planetary scales. A civilization capable of altering the composition of asteroids or comets could create fleets of messenger objects, each carrying encoded information in their molecular structure. Such messages wouldn't need to be complex literature or mathematical proofs. They might simply be signatures, unique chemical fingerprints, that announce the existence of their creators to anyone advanced enough to detect and analyze them. The extreme CO2 dominance of 3i Atlas could be such a signature, a molecular We were here left by a civilization that achieved spaceflight billions of years ago. This line of thinking connects to broader questions about convergent evolution and the potential universality of certain scientific principles. Just as terrestrial life discovered similar solutions to common problems, eyes evolved independently multiple times. Flight developed in insects, birds, and mammals. Perhaps intelligence throughout the galaxy tends towards similar methods of communication and exploration. If messaging through molecular composition is a natural strategy for advanced civilizations, we might expect to see certain patterns, objects with extremely unlikely compositions, isotopic ratios that deviate significantly from stellar nucleosynthesis, or molecular structures that seem too organized to be random. 3I Atlas, with its inverted Co2H2O ratio, could be our first detection of such a pattern. The speculation becomes even more intriguing when we consider the timing. 3 interstellar visitors in less than a decade, each with unusual properties, arriving just as humanity develops the technology to study them in detail. Could this be coincidence? Or might it represent the beginning of systematic contact? A gradual revelation designed not to shock or disrupt, but to slowly accustom us to the reality of galactic intelligence. Of course, the scientific method demands extraordinary evidence for extraordinary claims, and molecular messaging remains purely speculative. Natural processes can produce surprising chemical compositions, and the universe is vast enough to contain many statistical outliers. The unusual chemistry of 3I Atlas might result from formation conditions we don't yet understand, processing mechanisms we haven't considered, or simply cosmic luck in the lottery of planetary formation. Yet the speculation serves an important purpose in science. It expands our thinking about what's possible, and helps us design observations that might distinguish between natural and artificial explanations. If 3I Atlas does carry encoded information, how might we detect it? What patterns in composition, structure, or behavior might distinguish designed objects from natural ones? The molecular messaging hypothesis also highlights the importance of studying interstellar visitors with the most sensitive instruments available. Every spectroscopic measurement, every analysis of chemical composition contributes to our understanding of whether these objects represent natural phenomena or something more profound. We may be gathering evidence of galactic intelligence without yet realizing it. As we watch 3I Atlas continue its journey through our solar system, carrying its unusual chemistry toward an uncertain cosmic destination, we're reminded that the universe might hold forms of communication and intelligence that we're only beginning to imagine. Whether its molecular signature represents natural processes or something more intentional, 3I Atlas challenges us to think more broadly about the possibilities that exist in the vast spaces between stars. The chemistry that shouldn't be might, in the end, be exactly the chemistry that should be, if we're ready to read the messages written in molecules across the galaxy. Chapter 11. Worst case reframed as we reach the midpoint of our exploration into 3I Atlas. It's time to confront the question that has hovered at the edges of our investigation. What exactly constitutes the worst-case scenario for this interstellar visitor? We've established beyond doubt that 3I Atlas poses no physical threat to Earth. It will pass harmlessly through our solar system, never coming closer than a safe and respectful distance. The worst-case scenario isn't about asteroid impacts or extinction events. Instead, the true challenge that 3I Atlas presents is far more subtle and perhaps far more profound. It lies not in any danger to our physical safety, but in its potential to destabilize our understanding of our place in the cosmos. The worst-case scenario is that this ancient wanderer, with its impossible chemistry and mysterious origins, might force us to confront possibilities we're not prepared to accept. Consider what we've learned so far. 3I Atlas is old, potentially older than our entire solar system. It has survived a billion-year journey through the harshest environment imaginable, preserving within its structure chemistry that defies our expectations of how icy bodies should be composed. Its carbon dioxide dominance suggests formation conditions or evolutionary processes, unlike anything we understand from our own cosmic neighborhood. This combination of properties, extreme age, impossible survival, and anomalous composition, creates a profile that doesn't fit neatly into our current understanding of how the galaxy works. 3I Atlas is an outlier, an anomaly that highlights gaps in our knowledge and challenges assumptions we didn't even know we were making. The worst-case scenario is that 3I Atlas represents not an exception but a glimpse of a much larger truth, that the galaxy is far stranger, far more diverse, and far more active than our parochial solar system perspective has led us to believe. We've built our understanding of planetary formation, stellar evolution, and galactic dynamics largely from observations of our local environment. What if our neighborhood is the exception rather than the rule? This realization would force us to confront the uncomfortable possibility that Earth's development, the particular sequence of events that led to our planet's habitability and the emergence of life, might be far more unusual than we assumed. If the galaxy routinely produces objects with chemistry as exotic as 3I Atlas, it suggests environments and processes that operate according to rules we don't yet understand. The worst case extends beyond scientific uncertainty into the realm of philosophical discomfort. For centuries, human civilization has gradually expanded its understanding of the cosmos, while maintaining a sense of centrality and significance. We've learned that Earth orbits the Sun rather than vice versa, that our solar system is one among billions in the galaxy, that our galaxy is one among trillions in the observable universe. Each revelation has required us to adjust our sense of cosmic importance, while finding new ways to feel significant within an ever larger context. 3I Atlas threatens to accelerate this process of cosmic humbling. Its very existence suggests that our solar system, our comfortable, familiar, life-bearing oasis, might be a backwater, a quiet suburban neighborhood in a galaxy full of far more interesting and exotic phenomena. The chemistry that created 3I Atlas operates according to principles we don't understand, in environments we can barely imagine, under conditions that our models don't predict. Perhaps even more unsettling is the possibility that 3I Atlas might represent evidence of processes or intelligence that operate on scales beyond our current comprehension. The molecular messaging hypothesis, speculative as it remains, points toward the possibility that the galaxy hosts forms of intelligence that manipulate matter on planetary scales, that treat star systems as laboratories, that embed information in the very chemistry of wandering objects. The worst-case scenario is not that such intelligence exists. That would be a discovery of overwhelming positive significance. Rather, it's that such intelligence might exist on scales so vast and operate according to principles so alien that meaningful communication or understanding becomes impossible. We might be like microorganisms trying to comprehend the motivations of architects, aware that patterns exist, but unable to grasp their purpose or significance. This possibility touches on some of the deepest fears embedded in human psychology. The fear of insignificance, the fear of incomprehension, the fear that the universe operates according to rules we cannot grasp, or purposes we cannot fathom. 3I Atlas, with its ancient origins and impossible chemistry, serves as a reminder that the cosmos might be far stranger than we're comfortable contemplating. Yet there's also something liberating about this potential worst-case scenario. If 3I Atlas forces us to expand our understanding of what's possible in the galaxy, It also opens up new frontiers for exploration and discovery. Every challenge to our assumptions creates opportunities for new insights, new theories, and new adventures in understanding. The worst-case scenario, ultimately, is not catastrophic, but transformative. It's the recognition that our place in the cosmos might be smaller and stranger than we thought, but also that the cosmos itself might be richer and more wonderful than we dared imagine. 3i Atlas asks us to grow our perspective, to embrace uncertainty as a pathway to greater understanding, and to find excitement rather than fear in the recognition that the universe still has profound surprises in store. What 3i Atlas shows us is that the most unsettling collisions aren't with planets, but with assumptions. And so, as Part 2 begins, we step beyond the comforting boundaries of science into speculation, where possibilities stretch wider than the galaxy itself, and where the true implications of this ancient wanderer might finally reveal themselves. Chapter 12. Alien Probe Hypothesis. As we settle deeper into our cosmic contemplation, let's allow our minds to wander into the realm of possibility. What if Atlas isn't quite what it appears to be? What if this ancient wanderer, with its perfectly predictable orbit and reassuringly familiar chemistry, carries secrets more profound than we've dared imagine? The thought isn't new to us. When Oumuamua first tumbled through our solar system in 2017, whispers began almost immediately. Its elongated shape, its subtle acceleration as it departed. These anomalies sparked debates that echoed through observatories and laboratories worldwide. Could something so strange, so unprecedented, really be entirely natural? Now, as Atlas glides silently toward its closest approach with our Sun, similar questions stir in the quieter corners of scientific discussion. But here's what makes such the dilation both fascinating and challenging. If Atlas were indeed an artificial construct, a probe sent by some distant intelligence, it would need to be a masterwork of deception. Consider the requirements. This hypothetical probe would need to outgas carbon dioxide in precisely the right quantities, at precisely the right temperatures, to mimic a natural comet's behavior. Its trajectory would need to follow the gravitational laws so perfectly that no deviation could be detected by our most sensitive instruments. Its spectral signature would need to match, molecule by molecule, what we'd expect from a genuine interstellar wanderer. Such perfection in mimicry would represent technology so advanced, so sophisticated in its understanding of natural processes, that it would essentially be indistinguishable from the real thing. And perhaps that's the point. Perhaps the most elegant probe is one that whispers rather than shouts, that blends seamlessly into the cosmic background noise of natural phenomena. But here's what grounds us. Every piece of data we've gathered supports the natural explanation. Webb's detailed analysis reveals exactly what we'd expect from an ancient comet. Water ice sublimating away, carbon dioxide creating that characteristic coma, dust particles reflecting sunlight in patterns consistent with natural formation processes. The evidence aligns beautifully with our understanding of how comets behave when awakened by a star's warmth. Yet, the speculation serves a purpose beyond mere curiosity. By considering the artificial hypothesis, we sharpen our analytical tools, refine our detection methods, and prepare ourselves for possibilities we haven't yet encountered. We learn to distinguish between what the data actually tells us and what our imaginations conjure from the spaces between certainties. If Atlas were a probe, what would we hope to learn from such an encounter? Perhaps it would carry within its molecular structure a library of information about distant star systems encoded in crystalline matrices or complex organic compounds. Perhaps its very presence would be the message, a gentle announcement that we are not alone in our curiosity about the cosmos. But as we drift in this sea of speculation, we find comfort in returning to what we know with confidence. Atlas behaves exactly as a natural interstellar comet should behave. Its story is already extraordinary enough without artificial enhancement. A billion-year journey through the galaxy, a survivor of cosmic catastrophes, a messenger carrying the chemical signature of stellar processes we're only beginning to understand. Chapter 13. The dark forest scenario in the deepest hours of contemplation, when the universe feels most vast and mysterious. Some thinkers have proposed a chilling possibility about the cosmos around us. They call it the dark forest scenario, a name that conjures images of creatures hiding in shadowed woods, afraid to make a sound lest they draw the attention of predators. The idea flows from a simple but unsettling premise. Perhaps the universe isn't empty because life is rare. Perhaps it's quiet because survival demands silence. Imagine, if you will, a galaxy teeming with civilizations, each having learned through bitter experience that advertising one's presence is tantamount to signing a death warrant. In this dark forest of space, every star system might harbor intelligences that have discovered the harsh arithmetic of cosmic survival, that the safest civilization is the invisible one. The logic unfolds with crystalline clarity. Resources are finite, even on galactic scales. Any civilization advanced enough to traverse interstellar distances would possess technologies capable of reshaping entire solar systems. When such powers encounter each other, cooperation becomes a luxury that evolution rarely favors. The cautious survive. The bold become cautionary tales written in the cooling embers of dead worlds. If this scenario holds even a grain of truth, then our mysterious visitor Atlas takes on a different character entirely. Rather than a simple comet, following the elegant mathematics of orbital mechanics, it might represent something far more sophisticated. A scout designed to appear utterly, convincingly natural while gathering information about emerging civilizations like our own. Such a probe would need to be perfect in its disguise. It would masquerade as exactly what Atlas appears to be, an ancient comet, unremarkable in every measurable way, following precisely the trajectory that physics demands. Its creators would understand that the most effective surveillance is that which leaves no trace of its artificial nature. The carbon dioxide outgassing, the predictable orbital mechanics, the spectral signatures that match our models so precisely. All of this could be evidence, not of natural processes, but of technology so advanced it can mimic nature flawlessly. The probe would observe, record, and report back to its creators through methods we couldn't detect or comprehend. But here's what makes the dark forest scenario both compelling and ultimately unknowable. If it were true, we would expect to see exactly what we do see: apparent emptiness, natural-seeming phenomena, and a universe that maintains its secrets with careful precision. Yet as we float in this ocean of possibility, we find ourselves drawn to a different kind of peace. Whether Atlas is natural or artificial, whether the galaxy hides civilizations or truly stretches empty between the stars, our response remains fundamentally the same. We observe, we learn, we approach the unknown with careful curiosity rather than reckless broadcasting. If silence is indeed the price of survival, then perhaps Atlas represents not a threat but a teacher. It shows us how to move through the cosmos with grace and subtlety, how to gather knowledge without disturbing the delicate balance that might exist between civilizations we cannot yet perceive. In the end, the dark forest scenario reminds us that our place in the universe might be more precarious and more precious than we've dared imagine. And if that's true, then every moment of peace, every quiet night spent gazing at stars, becomes a gift to be treasured rather than taken for granted. Chapter 14. The Great Filter. There's a concept that emerges from the intersection of biology, astronomy, and existential philosophy, something researchers call the Great Filter. It's both a warning and a mystery, wrapped in the profound silence of space around us. Picture, if you will, the long journey from simple chemistry to spacefaring civilization. It's a path marked by countless steps, each one more improbable than the last. First, molecules must learn to replicate themselves with stunning precision. Then single cells must discover cooperation, forming complex organisms. Intelligence must emerge from neural networks. Technology must develop without destroying its creators. And finally, a species must learn to reach beyond its home world before some catastrophe ends its story forever. Somewhere along this progression lies a barrier so formidable that almost nothing passes through it. This is the Great Filter, the step that explains why the universe around us remains so mysteriously quiet, despite the billions of years available for evolution to work its patient magic. Perhaps the filter lies behind us. Maybe the emergence of complex cells, or the development of intelligence itself, represents such an astronomical improbability that Earth stands as a lonely exception in an otherwise sterile galaxy. If so, we are the miraculous survivors, the winners of a cosmic lottery so vast that we may never encounter another ticket holder. But there's another possibility, one that carries a chill like the deep space between stars. Perhaps the Great Filter waits ahead of us, hidden in our future like a trap we haven't yet learned to see. Maybe every civilization eventually reaches a point where its own success becomes its undoing. Nuclear weapons, climate collapse, artificial intelligence that escapes all constraints, or simply the gradual exhaustion of resources needed to maintain technological complexity. This is where Atlas enters our contemplation with particular poignancy. Imagine for a moment that our ancient visitor isn't merely a comet, but something else entirely. A relic of a civilization that once thrived around a distant star, now long since scattered to cosmic dust. Such artifacts would be the universe's equivalent of fossils, evidence of intelligence that once existed, but failed to navigate whatever filter claimed them. They would drift between stars for millions or billions of years, carrying within their structure the chemical signatures of worlds we'll never see, the molecular memories of civilizations we'll never meet. If this were true, then Atlas would represent both tragedy and hope. Tragedy, because it would stand as evidence that the Great Filter has claimed others before us. Hope, because it would prove that intelligence can create things that outlast even the collapse of civilizations. Messages in bottles cast into the cosmic ocean, waiting for someone else to find them and learn from their maker's fate. But whether Atlas is comet or relic, its presence reminds us of something profound about our own position in the universe. We stand at a unique moment in cosmic history, sophisticated enough to detect and analyze interstellar visitors, yet still fragile enough that our own future remains unwritten. The Great Filter, wherever it lies, teaches us humility. It reminds us that intelligence and technology, for all their power to transform worlds, carry no guarantee of permanence. Every civilization must find its own way through the labyrinth of existential risks that evolution and physics place in its path. As we watch Atlas fade toward its appointment with our sun, we're reminded that survival isn't just about avoiding asteroids or nuclear wars or climate catastrophe. It's about learning to think in cosmic timescales, to build institutions and technologies and ways of thinking that can persist across the vast stretches of time required for true interstellar civilization. Perhaps that's the real lesson our mysterious visitor brings. Not answers about alien intelligence, but questions about our own future among the stars. Chapter 15. Where is everybody? In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed a question that has echoed through decades of scientific thought. Where is everybody? He was referring to the absence of clear evidence for extraterrestrial intelligence, despite calculations suggesting that advanced civilizations should be common throughout our galaxy. This simple question has grown into what we now call the Fermi paradox. The puzzling contradiction between the high probability that alien civilizations exist and our continued inability to detect any signs of. It's a cosmic mystery that deepens every time we discover new exoplanets, every time we refine our estimates of potentially habitable worlds. The mathematics seem almost inescapable. Our galaxy contains hundreds of billions of stars. Many host planetary systems. A significant fraction of these worlds exist in the habitable zones where liquid water can exist. Given the billions of years available for evolution to work, intelligence should have emerged countless times across the cosmos. Yet, when we scan the skies with our most sensitive instruments, when we analyze the chemical compositions of distant atmospheres, when we search for the technosignatures of advanced civilizations, artificial lights on planet nightsides, massive engineering projects, the distinctive spectral lines of industrial pollutants, we find nothing but natural phenomena and the gentle whisper of cosmic background radiation. This silence becomes even more profound when we consider the timescales involved. If a technological civilization had emerged just a few million years ago in our galactic neighborhood, a blink of an eye in cosmic terms, they would have had time to spread across thousands of star systems, leaving traces we should be able to detect with current technology. Atlas fits into this puzzle as both evidence and enigma. Here we have an interstellar traveler, something that has journeyed across the vast distances between stars, carrying within its frozen chemistry the history of alien worlds. Yet every measurement, every spectral analysis, every careful observation confirms that it's exactly what it appears to be: a natural comet, shaped by physical processes we understand, following laws of physics we've verified countless times. In some ways, this naturalness is itself a kind of answer to Fermi's question. The universe may be teeming with travelers like Atlas, refugees from stellar evolution, debris from planetary system formation, nomads cast into the void by gravitational interactions we can model with our computers. But these are not the artificial constructs we've been searching for, not the technological signatures that would announce the presence of intelligence among the stars. Perhaps the silence has simpler explanations than we've imagined. Perhaps interstellar distances remain prohibitively vast, even for advanced civilizations, making expansion beyond single star systems a challenge that few species choose to undertake. The energy requirements for moving significant populations between stars dwarf anything in human experience. Projects that would require the coordinated effort of entire civilizations sustained across many generations. Or perhaps intelligence, once it reaches a certain level of sophistication, turns inward rather than outward. Maybe the most advanced civilizations discover that building virtual worlds and exploring inner space provides richer possibilities than the expensive and dangerous business of colonizing other star systems. There's another possibility that brings a different kind of peace to our contemplation. Perhaps we simply exist at the wrong time or in the wrong place to witness the galaxy's technological civilizations. Space is vast and time is long. The radio signals we've been broadcasting have traveled only about 120 light-years from Earth, a tiny bubble in a galaxy that spans 100,000 light-years. Any civilization that flourished and fell in our cosmic neighborhood before humans learned to use fire would be invisible to us now. Their technosignatures faded back into the natural background of space. As Atlas continues its journey toward perihelion, it carries this silence with it. Not the silence of emptiness, but the deeper quiet of a universe that keeps its secrets carefully guarded, revealing them only to those patient enough to listen for answers that may come in forms we haven't yet learned to recognize. Chapter 16. What would humanity do? Let us drift for a moment into the realm of carefully considered speculation. Imagine that tomorrow morning, astronomers announced with quiet certainty that Atlas isn't what it appears to be, that hidden within its seemingly natural chemistry lies evidence of artificial construction, proof that intelligence elsewhere in the galaxy has reached out to touch our solar system. How would we respond? What protocols exist for such a moment? Who would speak for humanity when humanity itself had to find its voice? The immediate response would likely cascade through established institutions with surprising speed. The International Astronomical Union would convene emergency sessions, coordinating observations and analysis protocols. NASA Planetary Defense Coordination Office would shift from monitoring natural threats to managing first contact procedures. The United Nations Office for Space Affairs would dust off documents that have waited decades for their moment of relevance. But beneath these institutional responses, humanity would face questions that have never been tested outside the realm of thought experiments. How do you verify claims that could reshape our understanding of our place in the universe? How do you distinguish genuine evidence from instrumental error, wishful thinking, or deliberate deception? How do you communicate findings that could trigger everything from religious revelation to economic panic? The scientific community would mobilize with unprecedented coordination. Every major telescope would turn toward Atlas. Every spectrometer would be recalibrated for maximum precision. Teams of experts would scrutinize data with the kind of methodical intensity usually reserved for Nobel Prize discoveries or space mission critical failures. The evidence would need to be overwhelming, undeniable, verified by independent groups using different instruments and different methodologies. Meanwhile, information management would become a delicate balance between transparency and responsibility. In our hyperconnected world, news travels faster than verification, and speculation can achieve global reach long before facts catch up. Government agencies would work to provide regular updates, clear explanations of what the evidence does and doesn't show, and careful context about the implications of various possibilities. The public response would likely span the full spectrum of human emotion and belief. Some would see vindication of long-held convictions about life in the universe. Others would experience profound shifts in their understanding of humanity's cosmic significance. Religious communities would grapple with theological implications, while secular thinkers would wrestle with philosophical ones. Fear would certainly emerge in some quarters. Fear of the unknown, of technologies beyond our understanding, of civilizations whose intentions we couldn't predict or control. But history suggests that curiosity might prove stronger than fear, especially if the evidence pointed toward passive observation rather than active threat. Communication attempts would begin almost immediately, despite the astronomical odds against success. Radio telescopes would beam carefully crafted messages toward Atlas's trajectory, mathematical sequences and prime numbers, and symbolic representations of human knowledge. Deep space network facilities would monitor for any anomalous signals that might represent a response. The psychological impact might prove as significant as any technological implications. For the first time in human history, we would know with certainty that intelligence exists elsewhere in the universe. This knowledge would reframe every conversation about our future, our responsibilities, and our potential. It would make concrete the possibility that our choices as a species echo beyond Earth, that our actions might be observed and evaluated by minds we've never imagined. International cooperation would face its greatest test, or would the magnitude of the discovery inspire unprecedented collaboration, a recognition that first contact belongs to all humanity, rather than any single country or institution. But perhaps most importantly, such a discovery would force us to consider what kind of species we want to be when we're no longer alone in our corner of the galaxy. How we respond to definitive evidence of extraterrestrial intelligence would reveal as much about humanity as about our cosmic visitors. As we drift back from this speculative exercise to our current reality, where Atlas remains a perfectly natural, perfectly fascinating comet, we carry with us a deeper appreciation for both the protocols we've developed and the questions we've not yet learned to ask. Chapter 17. Curiosity over containment in our imagined scenario of confirmed artificial intelligence aboard Atlas. One of humanity's most remarkable responses would likely be the very thing that's happening right now, in reality with our natural visitor: the triumph of openness over secrecy, curiosity over fear. Consider how the story of Atlas has actually unfolded. Within hours of its discovery by the Atlas telescope in Chile, data began flowing through international networks. Orbital calculations appeared in public databases. Observing coordinates were shared among astronomical communities worldwide. Rather than hoarding information or classifying discoveries, the scientific community opened its arms to collaborative investigation. This represents something profound about human nature that often gets overlooked in our more pessimistic moments. When faced with the unknown, our species' dominant response isn't to hide or hoard knowledge. It's to share discoveries as widely as possible, inviting verification, criticism, and contribution from minds around the world. The Hubble Space Telescope's observations of Atlas became available through public archives within weeks of being collected. Webb telescope data followed similar patterns of rapid dissemination. Amateur astronomers began tracking Atlas's progress using publicly available orbital elements. Citizen science projects invited participation from anyone with appropriate equipment and curiosity. This radical transparency stands in stark contrast to how we might expect governments or institutions to respond to genuinely threatening discoveries. There were no classified briefings about Atlas, no restricted access to observational data, no attempts to control the narrative or limit public knowledge. Instead, we witnessed something that might be uniquely human: the instinct to turn mystery into shared exploration. Even our speculative discussions about artificial intelligence in space follow this pattern of openness. SETI researchers publish their protocols for responding to confirmed extraterrestrial signals. Astrobiologists share their criteria for recognizing technosignatures in astronomical data. The scientific community has spent decades developing frameworks for verification and communication that prioritize transparency and international cooperation over national advantage or institutional control. This approach reflects a hard-won understanding that extraordinary claims require extraordinary evidence, and that such evidence emerges most reliably through collaborative scrutiny rather than isolated analysis. The history of astronomy is littered with discoveries that seemed revolutionary until independent verification revealed instrumental errors, misinterpretations, or wishful thinking. But the commitment to openness goes deeper than methodology. It reflects a philosophical stance about humanity's relationship with cosmic discovery. We seem to understand intuitively that knowledge about our place in the universe belongs to everyone, not just those lucky enough to operate the most powerful instruments or work at the most prestigious institutions. Consider the remarkable fact that anyone with internet access can download the same spectral data that professional astronomers use to analyze Atlas's composition. The observations that revealed its carbon dioxide-rich chemistry, its water ice sublimation, its dust particle characteristics. All of this information exists in public databases, available for independent analysis by anyone with the skills and interest to examine it. This democratization of cosmic discovery would prove crucial in any genuine first contact scenario. The verification process for claimed extraterrestrial intelligence would necessarily involve hundreds or thousands of independent researchers, each bringing different perspectives, different analytical tools, and different potential sources of error or bias to bear on the evidence. Even the trajectory itself, that elegant hyperbolic arc that carries it past our sun and back into the cosmic dark, provides clues about the gravitational environment where Atlas began its journey. Future discoveries promise to transform our understanding of these interstellar populations. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s, with the capability to detect objects much smaller and dimmer than anything we can currently track. Its systematic sky surveys will likely reveal dozens or even hundreds of interstellar visitors each year, building a statistical picture of what exists in the space between stars. This growing catalogue of interstellar objects will function as a kind of cosmic library, with each visitor contributing information about different regions of our galaxy, different epochs of stellar evolution, and different processes of planetary system formation. We'll begin to see patterns in their compositions, correlations between their trajectories and their chemistry, evidence of the various ways that stars and planets interact to send pieces of themselves into the galactic wilderness. Some of these discoveries will challenge our current understanding of how planetary systems form and evolve. Others will provide direct samples of material from stellar environments unlike anything in our own solar system. Still, others might carry organic compounds that formed in interstellar space itself, adding new chapters to our understanding of how complex chemistry develops in the cold, sparse conditions between stars. But, perhaps most importantly, the study of interstellar objects teaches us about the deep connectivity that exists across our galaxy. The carbon atoms in Atlas's carbon dioxide might have been forged in the nuclear furnace of a red giant star, dozens of light years away. The water molecules in its ice might have condensed from vapor in a stellar nebula when our solar system was still forming. The dust grains streaming from its surface might carry minerals that crystallized in environments completely unlike anything that exists on Earth. In this sense, every interstellar visitor serves as an ambassador from distant regions of space and time, carrying news of processes and environments that we can study in no other way. They remind us that our solar system isn't isolated from the rest of the galaxy, that we exist within a vast, interconnected web of stellar evolution, planetary formation, and gravitational dynamics that occasionally delivers pieces of itself directly to our doorstep. As Atlas continues its approach toward perihelion, it joins this growing library of cosmic knowledge, adding its own unique story to our understanding of how matter moves through space, how chemistry evolves in extreme environments, and how the patient processes of physics shape the structure and composition of our galactic neighborhood. This is the gift that interstellar objects bring us, not answers to questions about extraterrestrial intelligence or cosmic threats, but something perhaps more valuable: direct, tangible connections to the vast and ancient processes that created the galaxy we call home. Chapter 20. The Shape of Human Wonder. There's something profound and perhaps uniquely human in the way our species responds to cosmic mystery with such elaborate speculation, such detailed consideration of possibilities that may exist only in our imaginations. As we followed Atlas through both scientific analysis and speculative exploration, we've witnessed something remarkable about the shape that wonder takes in human minds. Consider how quickly our collective imagination transformed Atlas from astronomical object to cultural phenomenon. Within weeks of its discovery, it had inspired not just scientific papers, but also science fiction stories, philosophical discussions, and late-night conversations about our place in the universe. This rapid flowering of speculation around factual discovery reveals something essential about how human curiosity operates. We seem incapable of encountering mystery without immediately beginning to populate it with possibilities. An interstellar comet becomes a potential alien probe. Strange chemistry becomes evidence of exotic processes. Silence from space becomes either reassurance about our uniqueness or warning about dangers we haven't learned to perceive. This isn't a failure of scientific thinking. It's the engine that drives scientific thinking forward. The speculation serves purposes beyond entertainment or distraction. By imagining what Atlas could be rather than just what it appears to be, we prepare ourselves mentally and institutionally for discoveries that might someday require rapid, coordinated response. The protocols for first contact, the frameworks for analyzing artificial signals, the international cooperation needed for cosmic-scale problems, all of these emerge from our willingness to take speculation seriously enough to plan for contingencies that may never arise. But there's also something deeply creative, almost artistic, in how we construct these possibilities. The dark forest scenario doesn't emerge from data analysis. It springs from the intersection of evolutionary psychology, game theory, and poetic imagination. The Great Filter concept combines mathematical modeling with existential philosophy, and more than a hint of tragic storytelling. Even our most rigorous scientific speculations carry emotional undertones that reveal as much about human nature as about cosmic possibilities. This creativity serves another function. It helps us process the profound psychological challenges that cosmic discovery presents. The universe revealed by modern astronomy, vast beyond comprehension, ancient beyond imagination, mostly empty and apparently silent, can feel overwhelming to minds that evolved to navigate much smaller, more immediate environments. Speculation becomes a way of making the cosmic personal, of finding human-scale meaning in discoveries that dwarf all human experience. When we imagine Atlas as an alien probe, we're not just considering technological possibilities. We're grappling with questions about communication, intention, and consciousness that connect directly to our deepest concerns about connection and meaning. The fact that our speculations often prove wrong doesn't diminish their value. Oumuamua's strange behavior inspired theories about alien technology that subsequent analysis couldn't support, but those theories drove more detailed observations, more sophisticated modeling, and more rigorous criteria for distinguishing natural from artificial phenomena. The speculative process improved our actual scientific capabilities, even when the speculations themselves proved unfounded. Perhaps most remarkably, human wonder seems to scale naturally from the personal to the cosmic. The same sense of curiosity that drives children to ask endless questions about how things work also drives our species to build space telescopes, launch interplanetary missions, and spend decades analyzing the chemical composition of visitors from other star systems. This scaling suggests something hopeful about our potential as a cosmic species. If we can maintain our sense of wonder and curiosity as we encounter increasingly vast and complex phenomena, if we can continue to respond to mystery with creativity rather than fear, with collaboration rather than competition, then perhaps we possess the psychological tools needed for whatever cosmic challenges and opportunities await us. As Atlas fades toward its encounter with our Sun, it leaves us with this reminder. The capacity for wonder might be as rare and precious in the universe as the intelligence that creates it. In a cosmos that operates on scales and timelines that render most phenomena invisible to direct experience, the ability to imagine, speculate, and dream about possibilities beyond immediate evidence might represent one of consciousness's greatest achievements. The shape of human wonder, as revealed in our response to cosmic visitors, turns out to be both expansive enough to encompass the entire universe and intimate enough to connect us to our deepest concerns about meaning, connection, and our place in the vast community of existence. Chapter 21. Hope in Silence and Data. As our journey with Atlas draws toward its close, we find ourselves in a position to reflect on something remarkable that has occurred during these months of observation and analysis. What began as potential cause for concern, another mysterious visitor from interstellar space, has transformed into one of the most successful demonstrations of international scientific cooperation in recent memory. The response to Atlas's arrival showcases humanity at its collaborative best. Within hours of its discovery, astronomical data began flowing through international networks that span continents and cultures. Observations coordinated between ground-based telescopes and space-based instruments required split-second timing and unprecedented precision. The Hubble Space Telescope and James Webb Space Telescope worked in concert with facilities in Chile, Hawaii, and orbit, creating a distributed observation network that no single nation or institution could have achieved alone. But perhaps more importantly, the entire process has been marked by transparency that stands as a model for how our species might handle future cosmic discoveries of any magnitude. Raw observational data became available through public archives. Analysis techniques were shared openly in academic journals and preprint servers. Even preliminary results and speculative hypotheses were discussed in forums accessible to anyone with curiosity and an internet connection. This openness served multiple crucial functions. It allowed for rapid verification of unusual findings, preventing the kind of isolated errors that can lead to false alarms or missed discoveries. It distributed the analytical workload among hundreds of researchers worldwide, applying diverse expertise and different methodological approaches to the same dataset. Most importantly, it demonstrated that transparency can coexist with scientific rigor, that sharing information broadly actually strengthens rather than weakens the verification process. The transformation of potential worst-case scenario into genuine scientific understanding provides a template for how humanity might respond to future cosmic encounters that could be far more consequential than Atlas. We've demonstrated our ability to coordinate observations across international boundaries, to share data without regard for national advantage, and to reach consensus about complex phenomena through collaborative analysis, rather than competitive secrecy. Consider what this means for scenarios that might someday require more urgent response. If we ever encounter definitive evidence of extraterrestrial intelligence, if we discover asteroids on collision courses with Earth, if we detect gamma-ray bursts from nearby stellar explosions, the protocols and relationships established through cases like Atlas provide the foundation for effective Verhaltensweisen. Response. The scientific community has proven it can mobilize quickly when presented with unusual phenomena. The communication networks exist to share time-sensitive information rapidly and accurately. The verification procedures exist to distinguish genuine discoveries from instrumental errors or misinterpretations. Perhaps most importantly, the culture of cooperation has demonstrated its resilience, even when dealing with discoveries that capture intense public attention and media scrutiny. But beyond the institutional successes, Atlas's story reveals something profound about human psychology in the face of cosmic uncertainty. Rather than retreating into fear or conspiracy theories, the dominant response has been curiosity and wonder. Rather than demanding immediate answers to questions that require patient analysis, the public has largely embraced the gradual process of scientific discovery. This patience and trust in methodical investigation represents a remarkable achievement in an era often characterized by demand for instant information and simple explanation. The story of Atlas has unfolded over months, with each new observation adding detail to our understanding, without providing the kind of dramatic revelations that characterize fictional encounters with the unknown. Yet the public has remained engaged throughout this gradual process, finding genuine excitement in spectral analysis and orbital mechanics, in the careful accumulation of evidence, rather than the sudden revelation of secrets. This suggests something hopeful about our species' capacity to find meaning in scientific process rather than just scientific conclusions. As Atlas approaches perihelion and begins its fade back into interstellar darkness, it leaves us with this gift: proof that humanity's response to cosmic mystery can be marked by collaboration, transparency, and patience, rather than fear, secrecy, and haste. In a universe that may hold discoveries far stranger and more challenging than wandering comets, this demonstration of our better angels in action provides genuine reasons for hope about our future among the stars. Chapter 22. Good night, Cosmic Messenger. And so we come to the gentle close of our journey with Atlas, this ancient wanderer that has carried us through realms of science and speculation, certainty and wonder, fear and hope. As our mysterious visitor completes its closest approach to our sun and begins its long fade back into the cosmic dark, we find ourselves changed by the encounter in ways both subtle and profound. Atlas came to us as a stranger carrying secrets we couldn't immediately decipher. It arrived with the kind of trajectory that announces itself as definitively not from here, moving with velocities that spoke of billion-year journeys through the space between stars. In those early days of discovery, when we knew only that something unusual was approaching our sun, Atlas carried within itself all the possibilities that human imagination could conjure. Now, as it departs, it leaves us with something perhaps more valuable than the exotic discoveries our speculations had imagined. Atlas has given us a masterclass in how the universe actually works, not through dramatic revelations or sudden overturning of natural law, but through the patient accumulation of evidence, the careful verification of observations, and the gradual emergence of understanding from mystery. The carbon dioxide streaming away from Atlas's nucleus carries within its molecular structure the story of processes that occurred before Earth's atmosphere contained oxygen. The water ice sublimating in our sun's warmth preserves chemical signatures from regions of space we may never visit directly. Even the trajectory itself, that elegant hyperbolic arc that carries Atlas past our sun and back to the stars, encodes information about gravitational encounters that occurred when our solar system was still learning its orbital rhythms. But Atlas has taught us more than chemistry and orbital mechanics. It has shown us something profound about the nature of cosmic discovery, in an age when information travels instantly across our planet. But understanding still requires the patient work of careful observation and collaborative analysis. In a time when dramatic claims often outpace evidence, Atlas reminded us that the most profound truths often emerge gradually through the accumulation of small details rather than sudden revelation. The months of Atlas's approach and study have also revealed something hopeful about humanity's capacity to respond to cosmic mystery with curiosity rather than fear, with cooperation rather than competition. The international coordination that brought together telescopes across our planet and beyond demonstrated that some discoveries belong to all of us, transcending the boundaries that often divide our species when dealing with terrestrial concerns. As Atlas fades back toward the darkness between stars, it carries with it our radio signals, the accidental broadcasts that leak from our civilization and spread into space at the speed of light. In some poetic sense, we have marked Atlas with evidence of our presence, our curiosity, our collective effort to understand its nature and origins. It departs, knowing that intelligence exists here, in this small corner of the galaxy. intelligence capable of detecting and analyzing visitors from the void. The silence that will follow Atlas's departure is not the silence of emptiness, but the deeper quiet of patience. The recognition that the universe reveals its secrets on timescales that dwarf human experience, through processes that require more persistence than any individual lifetime can provide. Atlas has been traveling for 1 billion years to reach this moment of closest approach to our Sun. Its journey back to interstellar space will require another 1 billion years to achieve the distances from which it began. Yet somehow, in the brief cosmic instant of Atlas's passage through our solar system, we have managed to decode its chemical composition, trace its orbital history, and place its story within the larger narrative of stellar evolution and planetary formation. For this synchronicity, the arrival of an ancient traveler at precisely the moment when human civilization has developed the tools to study it, carries its own quiet poetry about consciousness, curiosity, and the rare privilege of bearing witness to cosmic processes. In the brief instant of Atlas's passage through our skies, we've traced its story, touched its chemistry, and listened to the echoes of its journey. It feels almost as if the universe allowed us this rare moment, a fleeting meeting between a wanderer of the stars and a species just beginning to understand its place among them. As Atlas drifts back into the darkness, we are left warmer, not colder, carrying a deeper patience, a greater wonder, and a quiet gratitude for the chance to listen. It reminds us that every visitor, no matter how brief, leaves a mark on our shared story. Safe travels, ancient traveler. Thank you for crossing our small corner of the cosmos. May your path remain steady in the silent night. And if your eyes are still open, know that another story waits just beyond this one. Perhaps not about Atlas, but about other mysteries that stretch across time and space. When you are ready, I'll be here to guide you into the next journey. I'm the Sleepy Professor, and I thank you for joining me on this journey. Until the next time we meet among the stars, take care, rest well, and keep wondering, and until our next story, may you rest well under distant stars.